Hello everybody and welcome to this, my corner of the internet. I am SD and this is the second episode in my series on OCR GCSE Computing. Today I'm going to be covering the hardware side of the syllabus, which is basically the things that are inside a computer. So let's get started. So first question is on my list, what is the purpose of a CPU? Okay, so basically the purpose of a CPU is to process data, and its main function is to fetch, decode and execute information and instructions from the memory. Okay, so the main three things that govern the performance of a CPU is its clock speed, its cache size, and the number of cores it has. And the greater than the amount of these things, then the better the performance of the CPU. Okay, so moving very swiftly on. Moving on to memory. So the first two types of memory in the book are RAM, which stands for Random Access Memory, is basically a temporary volatile store of data for the computer. So in it, so whilst the computer is on, it will store all of the programs that you have open. So in it will be stored the operating system and any applications that you have open. This allows the computer to multitask by loading data in and out of the RAM and from the cache memory, so that it can work on multiple. It can very quickly switch between the application it's working on, so it can maintain them and do processes in the background. Then virtual memory is an extension of RAM in the main memory. So onto your hard drive you can assign an area of virtual memory that allows if the RAM gets full, it can store things temporarily on the hard drive. So it's basically like an overflow car park at a shopping centre. If the main one gets full, it can overflow. More other new cars can be put into the overflow car park. ROM, which stands for read-only memory, is the non-volatile data store for all the instructions that make sure your computer starts up properly when you first switch it on, and it will tell the computer where to upload the operating system from, what the operating system is, and how to actually not blow up when you turn it on. I've mentioned it before, but the cache memory is a small amount of memory actually on the motherboard right by the CPU, which stores the information and the data and the instructions that the CPU is currently working on. So the operating system will take, and the CPU will take the data from the main memory, put it on the RAM, then when it's ready for it, it will move it from the RAM to the cache memory, process it, and then move it back to the RAM, and then if necessary back into the permanent storage. It's basically faster than the RAM because it's closer to the CPU. It's faster than the RAM, allowing for faster access and faster work. So flash memory is basically a development from what RAM is built from. So RAM works by having two knotted AND gates, so NAND gates, feeding into each other so that they maintain a specific charge whilst the computer is on. A flash memory basically improves that by in making sure that the charge is maintained across usages. So between the time when the computer is off and the computer is on, it will maintain that charge. It's basically been developed recently into solid-state drives, which are massive, and you can actually have them installed in your computer. They're a lot faster than the traditional magnet drive, which is basically a disk that is manipulated by magnets until they, in order to store either a 1 or a 0. Okay, so have a flash memory is slower than both RAM and ROM because it is not a part of the main system. It is usually in the form of a external hard drive. As storage devices become smaller and faster and capable of holding more, so for example, I have this memory stick right here. Okay, that is a memory stick, and that is 64 gigs, and yeah, it's very impressive. As memory becomes smaller and more portable and things, it actually allows for more innovative computers, because applications can be bigger and more processor heavy without the need for a massive computer, like the Colossus computer from World War II. Okay, so modern data is our computer is represented as binary, and that's ones and zeros. This is because it's the easiest way to do it, because a computer is made up of electrical components which can either have electrical current or not have electrical current. So therefore that can be expressed as either a 1 or a 0, on or off. It also allows data to be stored together with instructions side by side, so it improves memory management, so you can have a larger amount of stuff packed into your memory. So the way the computers work is they use logic gates, and there are 3 main logic gates that need to be known, and those are the AND gate, the OR gate, and the NOT gate. I'm not going to explain what they all do at the moment, but if you click the AND gate, I'm going to say it will take you to my video on how binary works. People test out logic gates by drawing these symbols out into logic diagrams, and these are basically just experiments in their head of how the computer is going to, how the circuit is going to work. They draw out what are called logic diagrams, which is what I'm going to draw for let's see, I'm going to use the example of A and B, okay, or not C. Okay, so that's 3 inputs, A, B, and C, put together, and they're going to create an output. So I'm using a bit of software called Logically, and this is the demo version, so it's free. I'm not splashing out on something that I'm not going to use very often. So just got my 3 inputs, which is switches, and I have given them all different names. Then I'm going to have an AND gate, and a NOT gate, a OR gate, and then a light bulb for an output, so you can easily see it. Okay, so we're just going to hook these up. So A and B are being put into the AND gate, and C is being put into the NOT gate. You then have the result of the AND gate going into the OR gate, along with the result of the NOT gate, and all those go out into the light bulb. And as you can see, currently the light bulb is off, because although C is off, it's being knotted to being on by the NOT gate, and then the OR gate is saying, hey, one of these is on, so one of them is on, so therefore my output should also be on. So if I turn off this, you can see the light goes off. If I turn this on, turn B on, nothing happens. But if I turn A on as well, the light comes on. If I turn C off, pardon me, the light stays on. And if I turn A and B off, it also stays on. So basically, this can be represented in what is called a logic table. A logic table is a written representation of the results of a logic diagram. So as you can see, each column, it represents either an input or an output, and each row represents a combination of inputs and their results. So as you can see, on the left hand side, I've put that A and B, the result of A and B is being put into column P, the result of not C is being put into column Q, and then the result of P or Q going into R. I've basically broken down the problem at the top of the page into different parts, which is a lot easier than doing it all at once. So as you can see, first let's just go through a couple of rows. So first one is A and B, as A, B and C are all 0. So A and B, neither of them are 1, so therefore P is 0. C is 0, so therefore Q becomes 1. P or Q, one of them, Q is a 1, whereas P isn't, but that doesn't matter, because one of them is a 1, you have R being the main output being 1. Let's go to, let's say, the middle one, where A is 1 and B is 0. C is also 0 in this case, so A and B, P is 0 because not both A and B are 1. C is then 0, so that gets knotted to 1. Q and R, Q or P or Q rather, one of them is a 1, so therefore the output is 1. Go to the last one as well. So as you can probably see, both A and B are 1, so therefore P is also a 1, and then C is a 1, so therefore that gets knotted to 0. But because the result of P is a 1, R is also a 1. Okay, so I hope that didn't get too confusing. So yeah, so let's see. Oh right, so you saw me talk about inputs there and outputs. So an input, these usually, on a large scale, we have input devices and output devices. So an input device is something like a keyboard or a mouse, and it inputs data into the computer. Okay, an output device is the other end. It allows us to, it's like a monitor or a speaker, and it allows you to receive the process data, the process data from the CPU. Okay, so let's see. So for example, a security guard's terminal would most likely have a keyboard and a mouse for it to control things. It would also have loads of cameras, so the security guard could see what's going on in the area they're protecting. Then it would also probably have as an output. It would then they would then have screens so they can then see what's going on. A shop assistant's terminal might have a computer which would have a mouse and a keyboard, but it could also have a touch screen as well as a barcode reader for obvious reasons, and a screen and a speaker for output. You have to remember though that a touchscreen is not an output. A touchscreen does not equal a screen. The touchscreen part of it is receiving signals from your fingers as to where your hands are on the screen. The screen, that's a bit of glass over the top of the actual screen, which is showing you the information. So don't get them confused. A touchscreen is not a screen. Okay, it's a bit of glass with electrical wires and a current going through it and everything. Okay, so the final example therefore would be a smartphone, which would have a camera, a microphone, a touchscreen, and maybe some buttons as some inputs, and then of course it would have a screen and a speaker as an output. Okay, so there are also special devices adapted for people with disabilities and special needs, and those are things like foot mice for people who are unable to move their hands properly, or eye trackers for people who eye trackers and things for people who can't move their bodies properly. and also I think there are braille keyboards for blind people, and also there's special dictation software that you can get for people who cannot coordinate their hands properly in order to type. Okay, so jumping back a little bit to memory, we've talked about primary memory, which is things actually on the motherboard, so the RAM, the ROM, and the cache. Now we're going to talk about secondary memory. Secondary memory is needed to store software and data between the times when the computer is on. So it's basically outside the motherboard of the computer. It can either be built in to the computer like your hard drive, or it can be external and plugged in using either the SD card slot in your computer or your USB stick, like this USB drive here. And basically common versions of this are things like the magnetic disk drive that most people have, which is basically a disk that is a metal disk that is manipulated by electromagnets, so the polarization of different points are either positive or negative, representing either 0 or 1. There are also things like solid state drives, which I've mentioned previously, which maintain a charge between usages rather than actually physically manipulating something. And in the past, people have also used magnetic strips, so in things like I can't remember what they're called now, cassette tapes, and also things like ticker tapes. That's really old. So that's Colossus times. Okay, so when considering to buy a solid state drive, a secondary storage device, you need to consider five main things actually. And those are capacity, which is how much data it can hold; speed, which is how fast it transfers data between the CPU or the inbuilt memory and itself, so how fast it transfers data. Portability, how easy is it to transfer from one place to another and take with you. Durability, how long does it last? And reliability. We talked about reliability in the last episode, and that's basically, is it likely to break or corrupt your data or just go completely haywire? So, for example, this memory drive here, 64 gigabytes, so that's a massive capacity. Speed, it uses USB 3, which is very impressive, which is the fastest, and it's like it can download a full-length movie in something like 40 seconds. It is fairly durable. It's got very good reviews on Amazon and things. And then reliability, well, I haven't had it long, but it has yet to completely stop working. So most computers these days will need about 64 gigabytes of space because of all the data that you'll generate using applications and things. And actually, your operating system will also take quite a bit of space. You also need to be able to transfer. It's best to have a faster memory because you need to be able to transfer data very quickly from one place to another. Durability, people are using their computers for longer and longer. It's advisable to have the computer should last you 5 years. You shouldn't buy a new computer every year because of environmental considerations and because you just don't generally need a new computer every year unless you're doing something ridiculous, like maybe you're a games developer and you need to have the best computer every year. You need to be able to you need to have memory which is small, so that you can get it from one place to another. Because people are, although we're actually, because then you can get more data into a smaller space. People are constantly on the move. So they need to be able to carry their devices with them, and they don't want to have a massive external hard drive that's about this big, weighing them down and dragging them back. And you also need to last a long time, as I said. and without it breaking or failing on you, because people need their data. People store all kinds of things on their computers, and things like servers and banks have your data on them, which need to be protected and secure and will last a long time. Okay, so my mouth is pretty dry, and I have actually now covered the entire of the hardware chapter of the book, only taking me 20 minutes. So yes, if you found this this episode helpful or interesting, make sure you like and subscribe. If you know somebody else who might find this helpful or interesting, make sure you share it with them, because I'm sure they'll be thankful for it, especially if they're doing this exam, which is a week tomorrow. Yikes. So yeah, there's not much else to say other than thanks for watching.